How's it going? So in this video here, we're going to be talking a little bit about the neuron, just a general overview, and we're going to talk about the different types of channels which are located on it and its main function. So if we take a look at this poorly drawn neuron here, one of its main functions is to generate an action potential. And so one is to generate an action potential, another is to transport neurotransmitters throughout this neuron. And so each neuron has three main components to it. We always have an input region here, we always have an axon region, and we always have an output region. And so if I were to label these for you, this is going to be our output region, this is going to be our axon, and this is going to be our input region. And so let's start with the input region. The input region is extremely important, and it has these kind of spiky looking things which I drew terribly, which are known as dendrites. And so the main function of our dendrites is they contain these types of channels known as ligand-gated channels. And so let me draw a ligand-gated channel for you over here. Kind of looks like this. Probably not in real life, but that's just how I draw it. And so let's imagine we have another neuron here, and this neuron here is going to be releasing its neurotransmitters. So we release our neurotransmitters here. Now every space between each neuron is known as a synapse. So we would have a synapse here, we would have a synapse here if we had another neuron here, like that. So let's go back here. And the main feature of a ligand-gated channel is that it's going to respond to neurotransmitters attaching to it. So when depending on the type of ligand-gated channel, if two neurons or neurotransmitters were to attach to this ligand-gated channel, it's going to open and it's going to allow for the influx of positive charge. And so the dendrites are extremely important because they have these types of channels on them. Now another function or important characteristic of our input region is we have a cell body. So each neuron is going to have its own cell body, and the cell body is going to be your typical cell body. It's going to have a nucleus, it's going to have an endoplasmic reticulum, Golgi apparatus, and so this cell body is going to be responsible for producing proteins or neurotransmitters. And so what's happening here is we have our nucleus, and depending on if it's a protein synthesized in the cytoplasm by a free ribosome or a protein synthesized on the endoplasmic reticulum is going to determine how quickly it can move down this axon. And so the cell body is very important for producing these neurotransmitters that we need to bring here to our output region. So if we go to our axon here, what we have in our axon in terms of transporting these neurotransmitters are microtubules. And so we have microtubules like this, and for each microtubule, we remember that it has its motor protein, which is known as a kinesin. A kinesin is going to move in the positive ended direction. So positive, negative. And so let's imagine we're producing these proteins, we're putting them in vesicles. This microtubule is going to be responsible for allowing this kinesin to transport these neurotransmitters to our output region over here. And so if you imagine we have these neurotransmitters in vesicles like that. So let's look at our axon region now. Our axon region has to be very important for generating an action potential. And so when we bring in this positive charge from these ligand-gated channels, once we get a certain amount of positive charge or reach our threshold, we're going to generate an action potential. So one main important characteristic of each axon is it's going to have something known as myelin sheath. And so this myelin sheath is going to be extremely important for insulating our neuron or increasing the speed of our action potentials down this axon. So between each myelin sheath, we're going to have our channels. And so on our axon, we're going to have a different type of channel. And this channel is going to be known as a voltage-gated channel. So we're going to have both Na plus voltage gated channels. And we're also going to have K plus voltage gated channels. And in my next video, we'll talk about what these channels do. But just know that these are voltage gated channels, and voltage gated channels are going to be responsible for allowing influx or efflux of Na plus or K plus, but they're going to be opening in response to membrane potential or charge. So let's say we generate our action potential all the way down our axon. Now we get to our output region. So our output region is also going to have a voltage gated channel, but this channel is going to be known as a calcium voltage gated channel. So if we were to draw a calcium voltage gated channel, and the calcium voltage gated channel is going to have a little bit different function. It's going to open in response to membrane potential or charge, but it's going to be responsible for allowing for the exocytosis of these vesicles. And by doing that, we're releasing these neurotransmitters into our synapse so that they can have their next function on this neuron.